Alright, so on this section we're looking at exploring discontinuities. You may notice that we skipped 1.8 and 1.9. 1.8 was supposed to be squeeze theorem, which I just included with 1.7 notes, and 1.9 is multiple representations, looking at graphs and tables and limits, and we have kind of been doing that as we go along. So today we're going to look at exploring discontinuities. And so this is really sort of a pre-cal sort of review. We're not going to use a lot of limit notation for this stuff today. We're going to sort of refine what we need to know using some limit notation tomorrow. So there are two different types of discontinuities that we're going to look at. The first type of discontinuity we're going to look at is a removable discontinuity. And a removable discontinuity is a hole in the graph. So whenever you have a hole in the graph, you could remove that discontinuity by just filling in that one point right there, and then the function would be continuous. Whenever we have non-removable discontinuities, these can look a few different ways. Non-removable discontinuities can look like jumps in the graph, so they might look something like this, where you have a jump in the graph. They also can be vertical asymptotes, so they might be something like this, maybe like this, a vertical asymptote there. So these are the two main ways that you'll see non-removable discontinuities. So what can cause a discontinuity? There are several things that can cause a discontinuity. A negative under the square root is going to give you a discontinuity. A 0 in the denominator of a fraction. A number that's less than or equal to 0 inside of a logarithmic function. A piecewise function that has a hole or a jump in it. And some trig functions are going to give you discontinuities, such as tangent, cotangent, secant, and cosecant. Those all have discontinuity. Sine and cosine are continuous. So what we're going to do is we're just going to go through and look at several different problems to tell what type of discontinuity we have and whether and where that discontinuity is at. So our directions here say find any x values for which f of x is discontinuous. Tell whether the discontinuity is removable or non-removable. So when we're looking at example 1 here, what we have is a fraction. And the fraction, we know we cannot have zeros in the denominator. So what we want to look at is we want to look at that denominator and we want to factor it out. To factor this denominator, I would start by factoring the 2 out. Factor out that greatest common factor. So you'd have 2 times x squared plus x minus 6. Technically, you don't have to do that, but it's going to make it a little bit easier to factor. And then x squared plus x minus 6 is also going to factor. So I could factor x, and we could do a plus 3 and a minus 2. So to sort of convey what we've got here a little bit more precisely, this is x plus 3 over 2 times x plus 3 times x minus 2. All right, so we know that anything that will give us a 0 in the denominator is going to be a discontinuity. So if we take this denominator and set it equal to 0, then we would have 2 equal to 0. That would not give us anything. We would have x plus 3 equal to 0, which of course would give us x equals negative 3. And we would have x minus 2 equals 0, which of course would give us x equals 2. So we have discontinuities at both of these places, x equals negative 3 and x equals 2. However, we also need to be able to describe what type of discontinuity we have at those points. So whenever we're dealing with rational equations, that means fractional equations here, if we have something that will cancel out, like the x plus 3 and the x plus 3 here, since that binomial cancels out, that tells us that we're going to have a hole in the graph at that point. So whenever we can cancel, that's a hole in the graph. So a hole is going to be here at x equals -3. And remember, those are called removable discontinuities. And then here we've got this x minus 2. That does not cancel out. So we are going to have a vertical asymptote here. And of course that is non-removable. Right? So that's what we're looking at these. We want to find those discontinuities and tell what type we have. Let's move on to example 2. Example 2, similar to example 1, except for we can factor the numerator and the denominator. So if we do that here for our g of x, this numerator will factor into x plus 2, x plus 3, and our denominator will factor into x plus 3 and x plus 1. Now, it's really important to note that the discontinuities only come from the denominator. So if we set this denominator right here equal to 0, we're going to get x equals -3 and x equals -1. We're going to have discontinuities at both of those places because that gives us a 0 in our denominator. We need to be able to describe these discontinuities. So this x plus 3 right here is going to cancel. So since that cancels, we know that this is a hole in the graph, or a removable discontinuity, and we would know that x equals -1. This is going to be a vertical asymptote. I'm going to shortcut that there for convenience, but know that stands for vertical asymptote. Now, this x plus 2 up here does not do anything. It does not tell us anything about discontinuities because we're only looking at the denominator. In fact, the only reason that we need to even factor the numerator is to see if something cancels in the denominator there. All right. Here are a couple more. Example 3 is a little bit strange. Y equals the absolute value of x plus 1 over x plus 1. I can know for sure that I'm going to have a discontinuity here at x equals -1 because -1 would make that denominator 0. However, at -1, I've sort of got a strange situation here because it looks like x plus 1 and x plus 1 should cancel, but I've got these absolute value bars here. So what I'm going to do is I'm going to kind of think of the table of graph of values here, so x and y. So if I approach -1 from the left, let's say I pick -4. Well, if I plug in -4, the absolute value of -4 plus 1 over -4 plus 1 is going to give me absolute value of -3 over -3, which gives me -1 here because that'll be +3 over -3. So this would be -1. -3, I would have absolute value of -3 plus 1 over that -3 plus 1. And in that numerator, I get absolute value of -2, which is +2. And then -3 plus 1 is -2. So you can see here, I'm going to get -1 again. And -2. Absolute value of -2 plus 1 over -2 plus 1 is going to give us 1 over -1. Again, -1. It's beginning to look like all the answers are -1. However, if I try to plug in -1, I would get 0 over 0, which we know is indeterminate, so I can't tell anything from that. If I plug in 0 here, if I've got the absolute value of 0 plus 1 over 0 plus 1, now I'm going to get 1 over 1, which is +1. And if I plug in 0 plus 2, which would be, I'm sorry, I changed the wrong thing there. If I plugged in, let's plug in 1. 1 plus 1 over 1 plus 1. Of course, here we're getting 2 over 2, which is also 1. And we can see that trend happening. It really is not going to matter what number we plug in. We're going to get 1 when we plug in those positive values. So I'm going to pull up Desmos here really quickly. And I'm going to graph this for us. So we've got here the absolute value, y equals, you can just type ABS for absolute value in Desmos, x plus 1 over x plus 1. And you can see what happens right here on the graph. We have, for all of our values below -1, our answer is -1. For all of our values of our x values above 1, our y value is positive 1. So we have this jump in the graph right here. So we would say that since this is a jump in the graph, that this is a jump which is non-removable. Now, that was kind of a lot of explaining just for that answer. You might be asking, why can't we just type it into Desmos immediately? And if it's calculator active, you can. But if it's not calculator active, which you may see on some of these, then you'll need to know how to do this. Also know you're going to have a jump in the graph anytime you have this phenomenon happening right here. So if I had something like y equals the absolute value of 2x minus 4 over 2x minus 4, this would also have a jump right there at, in this case, it'd be x equals 2, wherever that denominator equals 0. So you will see probably some more problems that look like this. All right, let's move on to example 4. We have a composition of functions here. So f of g of x, remember sometimes this is written like this, f of g of x. Sometimes it's written that way instead. So if you see something like that in your textbook, this is what it's talking about. This means we've got to plug g into f. So we're going to take g and plug it into f right there where the x is. So f of g of x equals 1 over x squared plus 3 plus 2. And so our f of g of x is going to equal 1 over x squared plus 5. So we're going to take that denominator, x squared plus 5, and we're going to set it equal to 0 because that's what's going to give us a discontinuity. And so we would subtract 5 from both sides. So x squared would equal -5. And then we could try to, why is it doing this? Stop it. We could, gracious. All right, there it goes. We could take the square root of both sides. But here's our problem. Over here we'll get x. But here we're getting plus or minus 5i because we have a negative underneath the square root. That is not a real answer here. That's not a real number. That's an imaginary number that we're dealing with here. So there is no real number that is going to make this denominator 0. You can see it does not matter what number we plug in here. We could plug in 1, 7, 8, -5, -1/2. It doesn't matter. Whenever we square this number, it's going to be positive. And then you're going to add 5 to it, which is a positive number. So it's going to be impossible for this to ever equal 0 using a real number. Therefore, we would say this one has no discontinuities. All right, let's move on. The next thing we're going to look at is piecewise functions. And for piecewise functions, we are looking at the intersections of the graph most of the time. So we can look at each separate equation separately, but typically when we have these pieces of the graph where they come together, that is where we're going to see discontinuities if we're going to have them. So if we're looking for discontinuities with piecewise functions, here I can see I've got x over 2, which remember is like 1/2 times x. So this is just you're not going to have a discontinuity here. This is just a line. You've got absolute value of x minus 1, which is that V shape. It's always continuous. You do have the square root of x plus 1. So underneath that square root, we know x plus 1 has to be greater than 0, greater than or equal to 0. That just means x has to be greater than or equal to negative 1. But if you look at your restrictions over here, we're only looking at this function for x is greater than 3. So we should not have any discontinuities for this either. So each piece of the piecewise function is continuous for its interval. But what we're concerned with is whether or not we are going to see these two pieces line up. So there is some notation that I want you to use for these, because we can't really say we can say f of negative 5. If we say f of negative 5, we mean that we're plugging in this negative 5 value here into this equation. But what we really want to know is what the limit looks like from the left and the right. So if we do the limit as x approaches negative 5, I'm just going to say of f of x, then from the left right there. So from the left, we would be looking at this function. I'm going to pull up Desmos again and graph this. So I can't remember how to do piecewise functions, so I'm just going to do y equals x over 2, and then we put, I think it's brackets like this, x is less than negative 5. Oh yeah, that works. I'm going to just do each piece separately, and y equals absolute value of x minus 1, and we put these brackets. Negative 5 is less than x less than 3. Technically, that should be a less than or equal to right there. Just for the graph, I'm not going to worry about that too much. And y equals square root of x plus 1, and that is for x is greater than 3. And so we can see here, if we're looking at the limit as x approaches negative 5 from the left, we're talking about this red function here, which is this graph right here for x is less than negative 5. So if I plug in negative 5 into that equation, I'm going to get negative 5 over 2. And you can see we're going to have a jump in the graph right here, because if I do the limit as x approaches negative 5 from the right, then that middle function is the absolute value function, and that's the function I'm going to use as I approach from the right. If I plug in negative 5 to that function, then I'm going to get absolute value of negative 5 minus 1. Sorry guys. Okay. Absolute value of negative 5 minus 1, which is absolute value of negative 6, which is going to give us positive 6. These two right here do not match. Therefore, we're going to have a jump, which is a non-removable discontinuity, at x equals negative 5. Okay. In pre-cal, we did a few of these problems, and I did not make you use limit notation because we did not know limit notation yet. But on the AP exam, if you're telling that something is discontinuous, then you have to use this limit notation right here. Technically, when we look at this tomorrow, there would be one more piece if it was going to be continuous we'd have to do. But for right now, we'll just look at these limits. So we also need to consider this point right here at 3, and you can tell from the graph it looks like this is probably continuous unless it's very, very close to being off. So if we do the limit as x approaches 3 from the left of f of x, from the left-hand side, right here is our 3. As we approach from the left, we would be on that absolute value function, which is the middle function. So that would be the absolute value of 3 minus 1, which is 2. And then if we do the limit as x approaches 3 from the right of f of x, we would use that bottom function, which is the square root of x plus 1. So the square root of 3 plus 1 would give a square root of 4, which of course would also be 2. So you can see that these two match. We also would need to check to make sure that that function value is defined. It actually is not. I didn't really mean for that to happen on this problem. Let's put an or equal to right here so that we have a open circle and a closed circle that fill each other in. And so it would be continuous here. So our only discontinuity for this one would be that jump at x equals -5. Let's try another one. So here we want to tell where this is continuous, and we have a little bit different notation right here. We've got the absolute value of x is less than 1. So when you see this, we did this, well, I don't know. We may have quit doing this in Math 1. I don't think I've taught it in the last couple of years because they took it out of the curriculum. But when you have an inequality with absolute value, to solve an absolute value inequality, as long as the absolute value is on the left, if you have a less than, that is going to be an and problem. If you have a greater than, or in this case greater than or equal to, that is going to be a or problem. I usually tell my students that greater is sort of sounds like greater. Less than does not, but greater sounds like or. So what we have here is we've got absolute value of x is less than 1. So that means x is less than 1 and x is greater than -1. Okay? Or another way that we can write that is -1 less than x less than 1. Okay? These are the values if you're less than 1 but greater than -1. Those are the values between -1 and 1. Okay, so this is really what they mean right here whenever they use this notation. Here we've got x is greater than or equal to 1 or x is less than or equal to -1. So with those absolute value, we are just restating without absolute value bars, and then we flip the sign and change the sign of this number here. So same thing here. Just write it the same as if the absolute value bars were not there at all. And for the second one, you're going to change the sign and make this negative here. So I really could rewrite this a little bit here. I could say f of x is typically, whenever we're looking at this, we're going to say that x is less than -1 would be the first thing. So we'd have x for x is less than or equal to -1. We would have cosine of pi x over 2 for -1 less than x less than 1. And then we just have our x for x is greater than or equal to 1. So what I've done here, because this is really two separate sections right here, I've just split those two up. And if you want to look at the graph for that, let's look at that really quickly. So we would have y equals x for x is, I'm just going to use the less than because it's easier to type, but of course that would be less than or equal to y equals cosine of pi x over 2 from -1 less than x less than 1. And then we would have y equals x, and x is greater than 1. All right, so we've got this graph right here. If I look at the graph, I can tell that I do not have, I've got discontinuities both at 1 and -1. But sometimes we will not have the graph. So what we would need to do is we would need to take our -1 that we have right here and plug it into both of these equations. We want to use limit notation when we do that. So we would say the limit as x approaches -1 from the left, that would be this function of f of x, would have to equal -1. But our limit as x approaches negative 1 from the right of f of x, that would be the cosine of pi times negative 1 over 2. So that's cosine of negative pi over 2. If you think of that unit circle, negative pi over 2 is right here. This is the coordinates of this point are 0, negative 1. Cosine is your x coordinate, so we'd have 0 here. These two do not match, so that tells us we have a jump at x equals negative 1. We also would need to look at our intersection right here at 1. So we would say the limit as x approaches 1 from the left of f of x. Right here from the left side, that would be cosine of pi times 1 over 2. So it'd be cosine of pi over 2. And pi over 2 falls right here. Coordinates of that point are 0, 1. The x coordinate is our cosine, which is still 0. And then we have the limit as x approaches 1 from the right of f of x, which of course if we're just plugging into x here just equals 1. These two right here do not match either, so we've got another jump at x equals 1. And remember, those jumps are also called non-removable discontinuities. Okay, here is another type of problem that we have. What's difficult about this problem is you've got the absolute value of x plus 2 is less than 4, and the absolute value of x plus 2 is greater than 4 for this one. So right here, you've got to kind of set this up first. So this is less than, so that's your and problem. So you'd have x plus 2 is less than or equal to 4, and x plus 2 is greater than or equal to negative 4. So this would be x is less than or equal to 2, and this would be x is greater than or equal to negative 6. So we'd be looking at negative 6 less than or equal to x less than or equal to 2. So that would be the section that we would use for 3x plus 1. Right here, we would have x plus 2 is greater than 4, or x plus 2 is less than negative 4. So here that's x is greater than 2, or x is less than negative 6. And x being less than negative 6, that's from here over, and x is greater than 2 from here over. And so those do not overlap. So if we wanted to, we could rewrite this the other way that we had. Now, you would have a lot of limit notation to check with this. Because this video is starting to get long, I'm going to shortcut it just a little bit. So we've got limit as x approaches. We got to worry about 2 and negative 6. So if we're approaching negative 6 from the right, then of f of x, then we would have 3 times negative 6 plus 1. And that, of course, is negative 18 plus 1, so that'll give us negative 17. That does not match 7, which I know that is what we're going to get from the other side here. If I do the limit as x approaches 2 from the left, from the left, f of x is going to be 3 times 2 plus 1. This does equal 7. So at 2, we're going to be continuous, but at negative 6, we are not. So we would have a jump or a removable discontinuity at x equals -6. All right, I think this is our last one here. Yep. So this is one more type of problem that you'll see fairly often. And we've got a piecewise function, and we're supposed to find the constants a and b such that the function is continuous on the entire real line. So I know that if these are continuous, if I plug -2 into both of these equations right here, so if we do that, we're replacing the x. So we'll have a times -2 squared minus b, and that will have to be equal to a times -2 plus 2 here. And so this gives me 4a minus b equals -2a plus 2. The problem here is I cannot solve this whenever I've got an a and a b in the problem. So I'm going to hold off there for a second. The other thing that I need to do is I need to take this 2 right here and plug it in. And if I plug the 2 into that middle equation, a times 2 plus 2 has to equal, there's no 2 to plug in here because we're replacing x with 2. There's no x here, so it'll just be b. This gives me 2a plus 2 equals b. Now, that equation also has an a and a b in it, so I'm kind of stuck. Don't have really anywhere to go on that problem alone. But with both of these together, I can do a system of equations. So this tells me that b equals 2a plus 2. So I could go over here and replace my b with 2a plus 2. So that'll give me 4a minus 2a plus 2 will equal -2a plus 2. And now this equation only has a's. So, all right, so we've got 4a minus 2a minus 2 equals -2a plus 2. And so 4a minus 2a is 2a minus 2 equals -2a plus 2. We could add this 2a, and I'm going to go ahead and add this 2 over here. So we get 4a equals 4, and so a is going to equal 1. So we found our a value. We need to be able to find our b value. To do that, we can just take our a value and plug it into this equation. So our b would equal 2 times 1 plus 2. So b would end up being 4 here. So if I plug in a 1 for my a and a 4 for my b, then it is going to make this entire function continuous on the entire real line. All right, the assignment that you're going to have for tonight is you're going to do page 96, and this is 37 through 57 odd, and then 63 and 65. 37 through 57, you're just looking for the discontinuities. So I was sort of fussing at some of you for not showing much work on some of those. These problems, especially some of the very first ones, are not going to be ones that require a lot of work. So 37 through 57, you're not going to have a lot of work for. 63 and 65 are going to require a little bit more work, so show a little bit of work on those. If you have any questions, let me know.